So we have seen that representation of BDD can be turned into a canonical form, and that is called ROBDD. Now let's suppose I want to convert a formula into ROBDD or do operation. Let's suppose I have two formulas in the form of ROBDDs. How would I take conjunction, disjunction, etc. So the algorithm maintains the following two global data structures. First, it maintains a store, and store, what it consists of is set of nodes. Initially it has two nodes, which is one is true and one is false. It has three maps, okay, high, low, and var. The low maps each node to another node, high maps to each node to another node, and var maps to each node to a variable name. Initially the map is empty. It means that if you give it any parameter, it will return null. Nothing is initialized. We also maintain a reverse map. It means that if I give you a variable and a pair of nodes, you can tell you which node was constructed using these variable and these two children nodes. Again, this notation means that this map is initially initialized to be empty, that if you give it any input, it will produce null. And slowly, as the data structure is built up, these will be changed. So let's see how we start building BDD. BDD is built by adding one node after another in your node store. There is a function we call make, which we will call make node, and it will construct a ROBDD node P with a small low child u0 and high child u. So if both the nodes are same, then again, because of definition of ROBDD, you return the child itself. You do nothing to build. If there is already node which was constructed using these three parameters p u0 u1, then you just look it up and return that node. You need to recreate it. If that is not the case, you create a node which we call u, and add it in that store. It just has three, which is labeled with variable p. u0 is the left child and u1 is the right child. And then also you need to record in the reverse map that using these three parameters, a node has been already created, and future you want to create again, then look it up and return the same object. Don't create again. How would you construct a BDD from a formula? So let's suppose you have a formula given f, and variable ordering is already specified. Then how do we go about building it? If number of variables is 0, if there's no variable in your formula, then either is equivalent to false or is equivalent to true. So you just check the equivalence, and then that you can obtain by the simplification, and then you obtain false or true. Or you can just project the formula into one not of p1 or p1, and then you call build ROBDD recursively, and then you build the node. Let us suppose we want to take conjunction of two formulas that are represented by ROBDDs u and v. How we go about taking their conjunction? Let's see. If the u is false, then you should return u clearly. If v is true, then taking conjunction with true shouldn't change anything, then you should also return v. Symmetrically, if u is equals to true or v is equals to false, then you should return v. Now moving on, let's define u0 u1 and pu, the variable and the children of the node u. Similarly, I define the node names with respect to node v. So if the labels is same, both nodes are labeled by the same variable, then you create a node with pu and take conjunction of the sub ROBDDs u0 and v0 using same function calling recursively, and similarly for u and v1, and make a new node. If u is labeled with a variable which is less than the variable which is labeling v, then what we have to do is that we need to pass on the same parameter on v. You cannot split on v anymore. You can split on u and go down, and we keep the same. This will allow us to respect the ordering of variables in ROBDDs. Symmetrically, if you have pu greater than pv, then we split on v0, not on u, and then we recursively call the function. One important bit to think about is how do we implement disjunction. In this function, you will see that the role of conjunction is not actually at all used here. These recursive calls are only based on if a variable was less and greater in both the nodes. So the only part which was relevant with respect to conjunction is here. That's the base case. By changing the base case, you can turn this algorithm into disjunction computing algorithm, XOR computing algorithm, or negation computing algorithm. Please try to work it out how it will work. So impact of BDDs. So in 90s, BDDs revolutionized the hardware verification. When it was first proposed, people didn't realize that it can be so useful, but once people start building this tool, and then it turns out to be very effective technology. However, by late 90s, in particular this paper, people found another way of doing satisfiability, which we know as a CDCL, and that marked the end of BDD era. So, however, BDD is still a heart of various software packages. In particular, you want to store, if you want to store a set of formulas, so representing a set of formulas is very efficient by a BDD. One may wonder is why BDD came to dominate the scene in 90s, and then later on they don't dominate anymore. So maybe this is because this is completely speculative. This may be because the computation resources in 90s allowed BDDs to be very effective at that time. But as soon as more computation resources were available, another algorithm which that much computing power became more effective. Once we will add few more zeros to our computing power, and maybe another algorithm will be far more effective than the algorithm we have right now. So what is the problem with BDDs? Why it is not as effective as CDCL in some situations? The basic fundamental problem with ROBDD is that it is trying to do too much. It all the time remembers all the satisfying assignment, exactly the set of assignments, and that is too much. It's overkill. At the end, once it finishes, it actually tells you the total number of assignments in a formula, and that you are looking for one assignment, and it's telling you all of them. That's sort of overkill. And second problem is the rigidity on the variable ordering. So once you fix your variable ordering and you build the BDDs, and you are taking conjunction, disjunction, doing several operations, then you may be wondering, oh, is my ordering bad? Should I reorder or not? And once you decide to reorder, it's a lot of work to reorder. And while this problem is not there in CDCL, very well reordering is often is a part of an optimization, and it is no rigid requirement to have a specific ordering. And that is the two key reasons why people say that the BDDs are not as effective as CDCL.